Welcome to the O-Level Chemistry lecture series. Today's topic is on stoichiometry and the mole concept. This is one of the most complicated concepts in O-Level Chemistry, and most students find that they stumble on this topic because there are several concepts involved and there are quite a lot of calculations involved as well. But don't worry, this is actually a very easy topic and I'll bring you through this topic for today. So there are a few things you will need to know in mole concept. It's all over here. So these are the main areas you need to know in mole concept. We will cover them one by one. This is a two-part lecture series. For part 1, we will cover all the way until the calculation without using equations, and in part 2 we will bring the equations to do the rest of the calculations. So let's start off with learning some of the basics of mole concept first, and we begin with calculating of MR and AR. So relative atomic mass, or AR, it represents the average mass of one atom of the element when compared to 1/12 the mass of an atom of carbon 12. So what does this mean? So for example, I have the AR of, say, magnesium 24. Okay, this is the mass of magnesium. I divide by 1/12 the mass of carbon, which is actually 1, and I get a value of 24. So this value of 24 is known as the relative atomic mass of magnesium. And if you refer to the periodic table, you will see that the 24 is on top and 12 is below. So this number, if you recall, is the proton number. This is the relative atomic mass. And AR has no units. Take a look, there's no units. You will observe that there's a few elements, or many of the elements actually have a AR which is not a whole number. So why is this so? This is because they are comprised of isotopes. And isotopes being atoms with different relative atomic masses will contribute to the overall AR value, and you will and the different percentages of the different isotopes actually give rise to the decimal places at the back. So let's take a look at checkpoint 1 here. I have chlorine 35 and chlorine 37, and it tells me that 25% is chlorine 37 and 75% is chlorine 35. So these two isotopes make up chlorine naturally. So let's work out what is the relative atomic mass of naturally occurring chlorine with 25% of chlorine 37 and 75% of chlorine 35. So this is a simple proportion calculation. AR of chlorine would simply be 37 times 0.25, so this is 25%, plus 35 times 0.75, this is 75%, and it will give me 35.5. If we work the other way around, given that the relative atomic mass of chlorine is 35.5 and there are two isotopes occurring in nature, what is the relative abundance of each isotope? So we let one of them be X first. So let's let the chlorine 37 abundance be X. Abundance be X. Which means that for chlorine 35, the relative abundance would be 1 minus X. So given that the AR is 35.5, so 35.5 will be equals to X times 37 plus 35 times 1 minus X. And solving, I will have X equals to 0.25. So this corresponds to a relative abundance of chlorine 37 as 25% and chlorine 35 as 75%. And this actually corresponds to the values on top here in the question here. 75% of it is chlorine 35 and 25% of it is chlorine 37. Similar question here. We have copper 63, which is 69%, and copper 65, which is 31%. Calculate the relative atomic mass of copper. So AR of copper is simply 63 times 0.69 plus 65 times 0.31, and I will have 63.6 for copper. The next part of this is the relative molecular mass. this is actually all the ARs for all the elements combined together. So for example, if I have H2O, I have H and I have oxygen, I have two hydrogens and one oxygen. I know the AR for hydrogen is 1.0. I know the AR for oxygen is 16. So the total relative molecular masses of the molecule is 1 times 2 plus 16, which is 18. Relative formula mass is used for ionic compounds. Same thing, we add up all the relative atomic masses in the ionic compound. For example, NaCl, Na is 23, chlorine is 35.5. Add them up and we have the relative formula mass of sodium chloride. Again, MR has no units. So let's do a quick checkpoint here. What is the MR of water? What is the MR of water? So first of all, we determine what is the formula of water. It is H2O. So step 1, we determine the formula of water is H2O, and then we can calculate the MR. MR is equals to 1 times 2 plus 16 equals to 18. So this is the MR of water. Do likewise for question 2A to 2J, and if you calculate them correctly, you should have the following answers. Ammonia, NH3, should be 17. Oxygen gas, O2, should be 32. Carbon dioxide, CO2, you should get 44. Glucose, you should have 180. Iron 3 hydroxide, FeOH bracket 3, you should get 73. Sodium hydroxide, NaOH, you should get 40. Hydrochloric acid, HCl, you should get 36.5. Sulfuric acid, H2SO4, you should get 98. Magnesium nitrate, MgNO3 bracket 2, you should get 148. And sodium carbonate, which is Na2CO3, should correspond to 106. This is a relatively simple part of the mole concept topic, so make sure you get this part right. Okay, the next part of this topic involves the calculating of percentage composition by mass. So this is the equation for calculating by mass. You notice that I use the AR of the element divided by the MR of the compound. So let's explore this equation through some simple worked examples here. So first of all, we have sodium chloride over here. So let's calculate the percentage composition by mass of the elements in sodium chloride. So step 1, we must determine what is the formula, and it is NaCl. Then now we can go about calculating the percentage composition by mass. So we have sodium and we have chlorine inside. So percent sodium will be equals to AR of the element, which is 23, divided by the MR of the compound, 23 plus 35.5 times 100%, and I will get 39.3% for percent of sodium. Percent of chlorine would be 35.5. This is the AR of chlorine divided by 23 plus 35.5, which is the MR of sodium chloride, times 100%, giving me 60.7%. This step can also be done in another way, because you know that NaCl comprises Na and Cl alone, which means that if I know Na is 39.3%, my percent of chlorine is actually 100 minus 39.3, and I will have 60.7%. So either way is okay. Both steps are okay. So do checkpoint 3, questions 2A to 2D by yourself. For 2A or iron 3 oxide, percent iron, you should get 70%. Percent oxygen, you should get the 30%. So this is Fe2O3. For 2B, sodium carbonate, Na2CO3, percent sodium, you should have 43.4%. Percent carbon, you should have 11.3%. Percent oxygen, you should have 45.7%. For copper 2 sulfate, CuSO4, percent copper you should have 40%, percent sulfur you should have 20%, and percent oxygen you should have 40%. And part D, potassium manganate 7, KMnO4. KMnO4, this should be 7, not 8. Percent potassium, you should have 24.7%. Percent Mn, you should have 34.8%. And percent oxygen, you should get 40.5%. If you can't get the respective percentages here, go back up, look through the worked example, question number 1. Okay, it is simply the AR of the element you wish to find divided by the MR of the entire compound. We now move on to the next part of the mole concept topic, percentage mass of an element or substance in a compound. So earlier we found the percentage composition. This part is similar to the percentage composition calculation, but instead of multiplying by 100, we now multiply by the mass of the sample, because this part gives us the proportion. So if we have the proportion and we have the mass of the sample, we can easily calculate what is the percent mass of an element. So let's take a look at this worked example here. Copper in 32 grams of copper 2 sulfate. So once again, step 1, we write down the formula, which is CuSO4. And now we can determine the mass of copper in 32 grams of copper 2 sulfate. So we need to determine the percent of copper first. The percentage of copper in copper 2 sulfate would be 63.5 divided by 159.6 times 100%. So this is the step for determining percent of copper. But now, since we know the mass of copper, and this is the proportion calculation, we could actually do it in a single step, like this. So percent mass of copper, mass of copper is equals to the proportion of copper in copper 2 sulfate multiplied by the mass of the copper 2 sulfate, and this gives us 12.7 grams. So notice here, this is the AR of copper, and this is the MR of copper sulfate. So this gives us the proportion of copper in copper 2 sulfate, and if I multiply by 32 grams, which is the copper 2 sulfate which I have here, it will give me the mass of the copper instantly. Try checkpoint 4 questions 2, 3, 4, 5, 6 yourself. I will go through question number 6. Question number 2, you will get 88.9 grams for oxygen. Question number 3, you should get 80.0 grams for carbon. Question number 4, you should have 36 grams for water. Question number 5, for question 5, you should get 79.8 grams for your water. And question 6, you should get the value of X as 7, if you got it right. So let's go through question number 6. 6 is a bit more complicated. You have a sample of hydrated iron 2 sulfate with this formula FeSO4.xH2O. This part here actually represents the water of crystallization. Okay, so the water of crystallization actually gives the structure to the crystals of copper of iron 2 sulfate, and we know that in this sample of hydrated iron 2 sulfate, 45.3% of it is water. So this is 45.3%, which means this is the rest of it, 100 minus 45.3. So we need to calculate the value of X. So we can do this in a very typical percentage mass calculation. So we know that the percentage mass of water is equals to 45.3%. So how do we calculate the 45.3%? It is simply the proportion of water, which is x times 1 times 2 plus 16, divided by the molar mass, divided by the relative formula mass of hydrated iron 2 sulfate, which is 56 plus 32 plus 16 times 4 plus x times 1 times 2 plus 16, and this one multiplied by 100%. I should get 45.3%. So if I solve this equation over here, I will have my value x equals to 7. So this is actually FeSO4.7H2O. So there are 7 water of crystallization per unit of iron 2 sulfate. If you recall earlier, you have seen copper sulfate dot 5H2O. So this is the what we call hydrated copper 2 sulfate, and this are the blue crystals we see in the lab. So when we remove the water of crystallization, we will get CuSO4, and this is what we call anhydrous copper 2 sulfate, and this is the white powder we see. Alright, so with and without water, they look very different. Okay, so we now move on to the proper mole concept section. So before we begin with the mole concept section, let's introduce to you a simple term called the mole. So the mole is used to describe or measure the amount of particles in a substance. So this particles can be atoms, can be ions, can be electrons, can be molecules, can be anything. Okay, it must be particles, so long as it is a particle. And we have this unit called MOL or mole. So let's say, how do we measure distance? Distance we measure with, maybe we can measure it with centimeters. So 1 centimeter, 2 centimeters, 3 centimeters. So what is the distance you have traveled? Maybe you have traveled 3 centimeters. So what is the number of moles present? What is the number of particles present? What is the number of moles present in a substance? It can be 1 mole, 2 moles, or 3 moles. Okay, take note that we do not have MOLS because even though it increases beyond 1, we do not have CMS, we do not have CMS. It is not 2 CMS, it is not 3 CMS, it is just 2 cm and 3 cm. So same for mole, it is simply MOL. This is a unit. You do not add S to a unit. So the first part of mole concept brings us to this equation here, which is 1 mole of any substance. Any substance will always contain 6.02 times 10 to the power of 23 particles. This is a constant. So if I have 1 mole of H2, I will have 6.02 times 10 to the power of 23 H2 molecules. If I have 1 mole of water, I will have 6.02 times 10 to the power of 23 water molecules. If I have 1 mole of iron, I will have 6.02 times 10 to the power of 23 iron atoms. If I have 1 mole of helium, I would have 6.02 times 10 to the power of 23 helium atoms, so and so forth. So long as I have 1 mole of a substance, I will always have 6.02 times 10 to the power of 23 of the particles. And this number, 6.02 times 10 to the power of 23, is also known as the Avogadro's constant. It was named after the scientist Avogadro because he discovered through experiments that 1 mole of anything, will always contain 6.02 times 10 to the power of 23 particles. So how do we make use of this number? We have this equation over here. So number of moles is equals to number of particles divided by Avogadro's constant. So let's say we have 1 mole of a substance. We would have 6.02 times 10 to the power of 23 particles. So if let's say I have 0.5 moles of a substance, how many particles would I have? It will be 6.02 times 10 to the power of 23 divided by 2. Okay, so this is quite simple. This is quite a simple application of mole concept here. We will slowly build up to the more complicated concepts at the back. So let's try checkpoint 5 first. We will do checkpoint 5, question number 1 together. How many moles of water molecules are there in 3 times 10 to the power of 24 molecules of H2O? So based on the above equation, number of moles equals to number of particles divided by Avogadro's constant. And with this, we will get 4.98 moles of water. So N actually represents number of moles. Small n represents number of moles. Do not write big N, this is wrong. Big N actually represents number of particles. So if you write big N and you write mole here, the whole thing is wrong. It is small n. Otherwise, you can spell out number of moles. Both ways are fine. So try the rest of checkpoint 5. Pause the video now to try the checkpoint. Question number 2. How many molecules are there in 0.25 moles of carbon dioxide? So again, this is a direct application of the equation. So number of molecules is simply 0.25 times Avogadro's constant, and we would get 1.51 times 10 to the power 23. For question number 3, calculate the number of moles of particles in so many atoms of hydrogen. So again, we use the same equation. Number of moles is equals to number of particles divided by Avogadro's constant, and we get 0.399 moles of hydrogen atoms. Question number 4. Calculate the number of particles in 3 moles of carbon atoms, 1 mole of ammonia, 20 moles of sodium chloride. This is simply using this equation again. Number of moles equals to number of particles divided by 6.02 times 10 to the power 23. So to calculate the number of particles, we simply take number of moles multiplied by the Avogadro's constant. And for A, we should get 1.81 times 10 to the power 24. For B, we should have 6.02 times 10 to the power 23. And for C, we should get 1.20 times 10 to the power of 25. Question number 5. How many molecules and how many atoms are present in 1 mole of hydrogen gas? So hydrogen gas is H2. How many molecules are present? Same equation. Number of molecules is equals to number of moles times 6.02 times 10 to the power 23. So it's 6.02 times 10 to the power 23. And H2 is actually made up of 2 hydrogen atoms. So how many atoms are present? If you were to split the covalent bond which holds the hydrogen atoms together, 1 H2 molecule actually gives us 2 hydrogen atoms. Okay, 1 H2 gives us 2 hydrogen atoms, which means that the number of atoms we have would be double that of the number of molecules, giving me 1.2 times 10 to the power 24 hydrogen atoms. The next part of this topic is on molar mass. Molar mass is essentially the same calculation process as determining the relative formular mass and relative molecular mass. You add the ARs together, but this case now we have a unit. So for water, for example, it is the way of calculating the relative molecular mass of water is taking 2 times 1 plus 1 times 16, you have 18. But now this is the molar mass and this is the mass of 1 mole. So the molar mass of water is 18 grams per mole, which means if I have 1 mole of water, it will be 18 grams. So conversely, if I have 18 grams of water, it means that it is equivalent to 1 mole. Right? So for NaCl, Na and Cl, Na is 23, Cl is 35.5, add together is 58.5, and molar mass units gram per mole. Let's do some simple calculations for 1A to 1F. So we do 1A together. For carbon dioxide, it is simply CO2. So it is 12 plus 16 times 2, and we have 44.0 grams per mole. If you do likewise for the rest of the questions, for N2, you should get 28 grams per mole. For N atoms, you should have 14 grams per mole. For copper 2 oxide, CuO, you should have 79.5 grams per mole. For calcium carbonate, CaCO3, you should have 100 grams per mole. For copper 2-sulfate pentahydrate, you should have 217.5 grams per mole. Basically, this is hydrated copper 2 sulfate. Okay, this is hydrated copper 2 sulfate, which is the blue color crystals. Right? Simple. Okay, now let's move on to the first formal equation in the mole concept. So number of moles is equals to mass divided by molar mass. So if I have one mole of water, I would have 18 grams. Correct? So how do I know it's 18 grams? Because the molar mass of water is 18 grams per mole. So if I have 2 moles of water, what is the mass of water I would have? It's simply 18 times 2, 36. So if I apply this in this formula, and I were to calculate the number of moles of carbon atoms in 12 grams of carbon, it is simply the mass of carbon divided by the molar mass of carbon. So I get 1.00 moles of carbon atoms for 12 grams of carbon. Right. And earlier we covered this first equation here, number of particles divided by 6.02 times 10 power 23, giving us number of moles. Mass over molar mass also gives us number of moles. So I can simply equate these two together, and I will have the combined equation here, which allows me to determine, say, the mass if I know the number of particles, or determine the number of particles if I know the mass. Right, so let's try checkpoint 7. Pause checkpoint 7. You can pause the video now and try checkpoint 7 by yourself. Continue the video once you are done. Checkpoint 7, question 1a. Calculate the number of moles of each of the following substances. So, based on the equation, number of moles for A, 10A. 1a, 10 grams of hydrogen gas. Number of moles is simply mass divided by the molar mass, which is 2. And I will have 5.00 moles. Okay, for part B, number of moles equals to mass over molar mass. H2O, this H2O, so it is 1 times 2 plus 16. I will get 2.22 moles. Sulfur dioxide is SO2. If you do likewise, calculation above, you will get 0.844 moles. And for part D, you should get 0.272 moles. For question 2A to D, calculate the mass of the following substances. So now you must calculate the mass, but it is exactly the same. Number of moles equals to mass over molar mass. If we know what is the substance, we can calculate the molar mass because it's simply the relative molecular mass or relative formular mass with a unit behind. So to calculate the mass, we simply take the number of moles multiplied by the molar mass. So for example, 2A, we have 3 moles of oxygen gas, so the mass would be simply number of moles multiplied by molar mass, which is 16 times 2, and we will get 96.0 grams. If you do likewise for the rest of the questions here, NO2, SiO2, Al2O3, for part B you should have 230 grams, part C you should have 210 grams, and part D you should get 510 grams. Question 3. Question 3 starts to bring in the earlier equation of number of particles divided by Avogadro's constant. So you are given 2.0 times 10 power 26 atoms of helium. You must calculate the mass. So once you see mass and you see number of particles, you must immediately think of these two equations. Mass divided by molar mass and number of particles divided by Avogadro's constant. So we are given the number of particles, and we know what is the molar mass because we know what is the substance in concern, which means that I can calculate mass simply by doing this multiplied by the molar mass. and I will have the mass of the substance. So let's do 3a together. So 3a would simply be mass equals to number of particles divided by 6.02 times 10 power 23. So number of particles divided by 6.02 times 10 power 23. This will give me number of moles multiplied by the molar mass of helium, which is 4, and I will get 1.33 times 10 to the power of 3 grams of helium. So if you do likewise for the rest of the question, for the rest of the part, 4b you should have 2292 grams, 3c you should have 42192 grams, and d you should get 84385 grams. Remember to round these three numbers into 3SF. Part 4. In part 4, it is similar to part 3, but instead now you're supposed to calculate the number of particles in each of the following substances. You are given the mass again. So once again, it is the mass over molar mass equation, because you are given the mass, and number of particles, so you need the number of particles over 6.02 times 10 power 23, and to calculate number of particles is simply mass divided by molar mass multiplied by this number over here. Okay, so this is a simple manipulation of the equation here. So let's do 4a together. You have 100 grams of chlorine gas. Number of particles of chlorine would simply be mass divided by molar mass, which is 35.5 times 2, multiplied by the Avogadro's constant. And you will have the value 8.48 times 10 to the power 23. If you do likewise for 4b to d, you should have 1.29 times 10 to the power 25 for b, 1.23 times 10 to the power 24 for c, and 4.12 times 10 to the power 24 for part D. So now let's move on to the next part of mole concept, which is learning on the chemical formula. Why do we need to know the chemical formula? Because if we do not know the chemical formula, we cannot balance the equation, we cannot count anything else. Okay, so you will have learned before chemical formula in Sec 2 or probably Sec 1 chemistry or science. So over here, we are introducing three more new terms here. Molecular formula. We are introducing three more new terms here. Molecular formula, structural formula, and empirical formula. So the molecular formula actually shows every single atom in the structure. So H2O, you have two H's and one O. The structural formula of water shows you the bonding in water, and the empirical formula is the simplest whole number ratio. So if we take a look at, say, hydrogen peroxide, molecular formula H2O2, every single atom in hydrogen peroxide, H2O2, there's two hydrogens and two oxygens. This is the structural formula, and empirical formula is HO. So how did I get the HO? This is the simplest whole number ratio. So if we see H2O2, there is a common multiple of 2, which means that if I divide by 2 throughout, I will get H1O1. 1 I do not write in because 1 is simply 1, so I just write HO for here. For butane, C4H10, the common factor throughout is 2. So if I divide by 2, I will have C2H5. Right? And the thing about empirical formula is that it can be calculated using data from experiments. And from the empirical formula, we can work backwards to give us the molecular formula of the compound. So let's take a quick look. In this example, we have 0.48 grams of magnesium being burned in oxygen to produce 0.80 grams of magnesium oxide. We need to determine the empirical formula of magnesium oxide. So how do we go about doing this? It's actually very simple. So first of all, we know that I have 0.80 grams of magnesium oxide, and I have 0.48 grams of magnesium. So where did the extra mass come from? If you look at the question, it says that magnesium was burned in oxygen, which means the extra mass in 0.80 must have come from the oxygen. So what is the mass of oxygen? That was incorporated into magnesium oxide, it is simply 0.80 minus the magnesium that was used. And this gives us a value of 0.32 grams. So once we have this, we can calculate the empirical formula of magnesium oxide. So how do we go about doing this? MgO, we draw a simple table. The mass, we fill it in, 0.48, 0.32. Next step, we take the mass divided by the AR, and we have 0.0198 and 0.0200. The next step we do is to determine the mole ratio. To calculate the mole ratio, we take the smallest number here and we divide throughout by the smallest number. So over here we see that the smallest number here is 0.0198. So the mole ratio is simply 0.018 divided by 0.0198, 0.0200 divided by 0.0198, and for this I have 1.00 and I have 1.01. This is the mole ratio, but this is not the end yet. We convert this to the simplest mole ratio, and the simplest mole ratio must be a whole number. So this is 1, and we round this to 1. So we know that there's 1 unit of Mg for every 1 unit of oxygen, which means that the empirical formula for magnesium oxide is simply MgO. Okay. Number 2, this sample of gaseous oxide of nitrogen contains 30.4% of nitrogen and 69.6% of oxygen by mass. So how do we determine its empirical formula? It's the same. We know there's N, we know there's O, we know percent mass is 30.4 for N and 69.6 for oxygen. We take percent mass divided by the AR, 14, 16, and we get 2.17 and 4.35. Next step is to determine the mole ratio, and the mole ratio is calculated by taking the smallest number and dividing it throughout. Dividing this throughout, we have 1.00 and 2.00. And now the last step is to determine the simplest mole ratio, and this is the whole number. So we round 1.00 to 1 and 2.00 to 2, which means that our empirical formula for this oxide of nitrogen is NO2. Easy enough. Let's try checkpoint 8 by yourself. Pause the video now and try checkpoint 8. Continue the video once you are done. Alright, so for checkpoint 8, 8A, this one is a simple calculation. You should have CH2. 8B is a bit more complicated. 8B is actually quite easy as well. You should get NO2. 8C is a complicated one. 8C, if you counted it correctly, you should get Al2O3. If you counted it wrongly, you will get ALO. This is the wrong one. So let's go through checkpoint 8C together. A 6.2 gram sample of aluminum oxide was analyzed and it was found to contain 3.28 grams of aluminium, which means that the rest of the mass must belong to the oxide portion or the oxygen portion. So we can determine the mass of oxygen in aluminum oxide by taking 6.20 minus 3.28, and I will have 2.92 grams of oxygen. The next step will be to draw the table out. Aluminium oxygen, 3.28 grams, 2.92 grams. This is the mass. Then we take mass, divide by AR. This is 27. This is 16. And I will have 0.121 and 0.183. Then mole ratio will be to take the smallest number and dividing it throughout. And this smallest number is 0.121. And I have 1.00 and 1.51. So this is the crucial step now. Can we round 1.51 to 1 or 2? No, we can't. The rule for rounding is as follows. If it is less than 0.2, we can round down. If it's more than 0.8, you can round up. For example, 1.19, you can round to 1. 1.2, you cannot round to 1. 1.8, you cannot round to 2. 1.81, you can round to 2. So in this case, how do we get a nice whole number for the simplest mole ratio? We simply multiply throughout by a integer, the smallest possible integer, to make the mole ratio as close as possible to a number which can be rounded. So in this case, we can multiply by 2. And we have 2 here and 3.02, which gives us a very good approximation to 2 and 3. So this gives us the empirical formula of aluminum oxide as Al2O3. Alright, take note, do not round 1.51 down or up. Multiply by integer, by the smallest possible integer, to bring it to a number which can be rounded. Okay, so part D, if you calculated correctly, you should get sodium carbonate Na2CO3, and part E, you should have Cl2O, dichlorooxide. So after learning about empirical formula, it brings us naturally to the next part, which is the molecular formula. So the molecular formula is actually derived from the empirical formula. How so? Let's take a look at the example here. So over here, I have a gaseous oxide of nitrogen which contains 30.4% nitrogen and 69.6% oxygen. So with having these values with us, it means that we can calculate the empirical formula of this nitrogen oxide. And I also have the molar mass of the oxide being 92.0 grams per mole. So if we think about this, H2O2, this is the molecular formula. The empirical formula would be HO because I've divided by 2 throughout, correct? So if I know that the molar mass of hydrogen peroxide is 1 times 2 plus 16 times 2, which is 2 plus 32, which is 34. The empirical formula would give me a relative molecular formula of 17. Correct? So this is actually 2 times. Times 2, I will get 34. Why times 2? Because it's H2O2. So in this same fashion, if I determine what is the empirical formula of hydrogen peroxide, and I know what is the molar mass of hydrogen peroxide, the real molar mass, I will be able to calculate this value out. So once I have this value, I will be able to determine what is the molecular formula. So let's calculate for this example over here. For N and O, this is 30.4% and this is 69.6%. So this is the percent mass. So next step is the percent mass over AR, and I have 30.4 divided by 14 and 69.6 divided by 16, giving me 2.17 and 4.35. Next step is to calculate the mole ratio, which is simply dividing throughout by the smallest number, and this is 2.17, and I have 1.00 and 2.00, and my simplest mole ratio would be 1 and 2. So I have the empirical formula of NO2. So based on what I explained earlier, to calculate the molecular formula, we simply let the molecular formula be NO2 bracket n, because n is the common factor which we divided out earlier. So now we must multiply n back in to NO2's formula. So what we can do here, based on this, you see, I've used individual ARs of the elements here, and I've calculated 34. Over here is the AR elements as well, and I know I must multiply by 2 to get back my 34. So same case here, 14 plus 16 times 2 times n equals to 92.0. And solving, I will have n equals to 2. So based on this, I will be able to determine the real molecular formula of this oxide of nitrogen, and it is actually N2O4, dinitrogen tetroxide. Dinitrogen because it's 2, tetra because it's 4, so it's dinitrogen tetroxide. Okay, attempt checkpoint 9 by yourself. This is quite simple. Pause the video now. Continue with the video once you are done. For checkpoint 9, the first one, the molecular formula, if you counted correctly, you should get C3H6O3. The value of n is equals to 3. For question number 2, if you calculated it correctly, you should have n equals to 2, giving you C2H6O2. If you can't get any of these molecular formulas here, please go back to the worked example on top, rewind the video, and watch through how I determine the molecular formula from the empirical formula calculation. Now let's move on to the next part of this mole concept topic, molar gas volume. This is the simplest part of mole concept, in fact. So it relates between the number of moles of a gas and the volume of a gas. So this equation here, number of moles is equals to volume of gas divided by 24. Why? Because 1 mole of any gas, 1 mole of any gas will always occupy a volume of 24 dm cube at room temperature and pressure, or we call this RTP. So 1 mole of any gas always be 24 dm cube. So if I have 1 mole of hydrogen gas, I will have 24 dm cube. If I have 1 mole of oxygen gas, it will be 24 dm cube. If I have 1 mole of water vapor, it will also be 24 dm cube. So 1 mole of any gas, regardless of the formula, will always be 24 dm cube. So with this, how do we calculate the number of moles of 48 dm cube of hydrogen gas? Very simple. Number of moles is simply volume over 24. So volume is 48 here, divided by 24, we will get 2.00 moles of hydrogen gas. Now, pause the video here to try checkpoint 10. Continue the video once you are done. So for checkpoint 10, 1A, very simple. Number of moles, you must calculate the volume at RTP. So use the equation number of moles equals to volume over 24. So for 1A, 0.5 equals to volume over 24, and you should get volume equals to 12.0 dm cube. So if you do likewise, 1B you should get 24.0 dm cube, and for 1C you should get 72.0 dm cube. Question number 2. Calculate the number of moles at RTP of the following: 50 dm cube of carbon dioxide, and so forth. So now, this is the other way around. Again, it's the same equation, number of moles equals to volume over 24. So now the volume is given to us, but the number of moles is not given, and we need to calculate the number of moles. So let's do for 2A. So for 2A, number of moles equals to volume over 24. I have no idea what's number of moles, but I know the volume is 50 divided by 24, and I will get 2.08 moles. For 2B, notice this is given in cm cube, and the 24 here is in dm cube. So we will need to convert the volume into dm cube first, or we can convert 24 into cm cube. So we know that 1 dm cube is equals to 1000 cm cube, which means that 4000 cm cube I must divide by 1000 to give me dm cube divided by 24, and I will have 0.167 moles. If you do likewise for 2 part C, you will get 2.67 moles of hydrogen chloride vapor, or HCl. Okay, so now that we have covered the three equations in mole concept, we can actually link them all together. The first one we covered was number of particles over Avogadro's constant. The second one was mass over molar mass, and the third one was volume over 24. All these individual equations is equals to the number of moles. Is equals to number of moles, equals to number of moles, equals to number of moles. So I can put them all together, and based on the variables given in the question, I can calculate any of the items I want in the equation. So let's test this out on checkpoint 17's questions. Pause the video now and attempt checkpoint 17. Alright, so for checkpoint 17, question number 1a. A sample of sulfur trioxide has a volume of 6 dm cube RTP. We must calculate the amount of SO3 molecules. This is quite simple. 1a is simply number of moles equals to volume over 24, 6 divided by 24, and I will have 0.250 moles. For part B, to calculate the number of molecules, now we use the number of molecules equation. So number of molecules equals to number of moles equals number of molecules divided by Avogadro's constant. If I sub in the values here, I will get my number of particles as 1.51 times 10 to the power 23. And for part C, it is quite simple. The mass, I simply use mass equals to number of moles times molar mass. And I have 0.250 times sulfur trioxide, and I will get 20.0 grams. So this equation is actually the number of moles equals to mass over molar mass equation. Okay, so I shifted this to multiply together to give me the mass of sulfur trioxide. Question number 2, pretty simple as well. I have the mass of gas and I have the volume of the gas. So I now need to determine the identity of gas X. So how do I know what is the gas X? I must determine what is the AR of gas X, because from the AR I can look at the periodic table and I will be able to see what is the value of gas X. Then I will know what is X. Okay, correction, earlier it should be checkpoint 11, not checkpoint 17. So now let's calculate what is, let's try to determine what is gas X over here. So what values do we have here? We have the volume of the gas and we have the mass of the gas. So we can calculate the number of moles of X as volume, convert this to dm cube, and I have 25 moles. So if I have the number of moles and I have the mass, I can use number of moles equals to mass over molar mass. This equation here. I have number of moles, I have mass. So I can count this very easily. So the molar mass of X is simply number of moles multiplied by the molar mass is simply mass divided by the number of moles. And I have 4 grams per mole. Okay, so mass, number of moles, molar mass. So if I do a simple manipulation, I get number of moles equals to mass divided by the number of moles. And I have 4 grams per mole. So if I refer to the periodic table, I will be able to see that this is helium-4. So gas X is actually helium gas. Okay, so let's move on to the next part of mole concept, which is on concentration. This is a very simple part. So let's think about this before we go into concentration. Let's think about this. If I dissolve 10 grams of salt, in 1000 cm cube of water. This is actually 1 dm cube. What is my mass of salt in this volume of water? It is simply 10 grams per dm cube. Correct? Because I have dissolved 10 grams inside 1 dm cube. So in 1 dm cube, how much do I have? I have 10 grams. So concentration is basically telling us what is the mass or what is the amount of solute per unit volume of a solution. And there are two main ways in which we go about doing this. We have the mass per unit volume, or we have the number of moles per unit volume. So this is simply mass divided by volume, or number of moles divided by volume. So let's take a look at the example here. I have 50 grams of NaOH pellets and I dissolve in 1500 cm cube of water. I must calculate the corn in mole per dm cube. So where is the mole here? This is the mass. So step 1, I must convert the mass into moles. So number of moles here is equals to 50 grams mass over molar mass, 23 plus 16 plus 1, and I have 1.25 moles. So the concentration of NaOH, square brackets is used to represent concentration. Okay, this square brackets, it is simply the number of moles divided by the volume. Convert this into dm cube by dividing by 1000, and I have 0.833 moles per dm cube. If I wanted to convert this into grams per dm cube, we can simply do a multiplication of what? So let's take a look. Number of moles equals to mass over molar mass again. So in this unit here, it is moles. So to get my mass out, I simply take the number of moles multiplied by the molar mass. So if I take 0.833 multiplied by the molar mass of sodium hydroxide, 23 plus 16 plus 1, I will have the concentration in gram per dm cube. So to revert from this to this, I simply take the concentration in gram per dm cube and I divide this by the molar mass of sodium hydroxide. Let's attempt checkpoint 12 by yourself. Pause the video now and attempt checkpoint 12. Okay, checkpoint 12, 1A. I have 40 grams of sodium carbonate dissolved in 500 cm cube of water. I must calculate the corn in mole per dm cube. So let's do 1A together. So the corn of Na2CO3 is simply the number of moles, which is mass over molar mass. 23 times 2 plus 12 plus 16 times 3 divided by the volume of water converted to dm cube, and I have 0.755 moles per dm cube. Okay, if you do likewise for B, you should get 0.744 moles per dm cube. For 1C is a bit different. This is 1000 cm cube of HCl bubbled, which means that HCl is a gas. So to calculate the amount of HCl, it is the volume of HCl divided by 24. So this one gives us the amount of HCl, and the rest the same. I divide by the volume, convert to dm cube, and I will have 0.0139 moles per dm cube. Take note, read the question carefully. This is a gas, so we use the gas equation to calculate. Question 2. Calculate the amount of H2SO4 in 1200 cm cube of this concentration of dilute sulfuric acid. So this is simply a manipulation of the equation. So concentration is equals to number of moles divided by the volume. So if I have the volume here and I have the concentration here, number of moles is simply concentration multiplied by the volume in dm cube, because this is in dm cube, so I must convert this into dm cube by dividing by 1000, and I will get a value of 0.600 moles. If you do likewise for question 3, you will get 18.5 grams. So how do we get the mass value out? Over here with the moles value. So once you have the mole, number of moles equals to mass over molar mass. You simply convert the moles into mass by multiplying by molar mass. You should get 18.5 grams. And question number 4, if you do likewise, you will actually get 22.4 grams of potassium hydroxide, KOH. So we have come to the end of part 1 of mole concept. Look through the videos again if you are not very sure, because in part 2 we will be covering even more calculations, and it is based on the chemical equations. So see you in part 2 of mole concept.